Dealing with loss. So predictive models and data science applications begin with data. Training data, M, observations, features T sub I and responses Y sub I. T sub I is in Rn. It has to be in some vector space. And if we're doing classification, our response is a label or class. If we're doing regression, it's a vector. Testing data is our gold standard. It's what we use to test the model once we've used the training data to create it. And typically we split the training data into training and validation sets so as to produce the best possible model. And a function model predicts Y sub I, the response. So remember, our model is a function with parameters. It's actually a family. In vector notation, it looks like this. And it's also a layer. The parameters are in the layer. And if we're given a training sample, an observation, the forward of the model on that observation for fixed parameter values is denoted Y hat sub I. So we fix the parameter values. We have an observation. It goes through our layer in the forward direction and gives us a prediction. A loss function measures how close Y hat sub I, the prediction, is to Y sub I, with the loss function Y hat I Y sub I 0 if and only if the two are the same. So loss functions are used to define costs, where a loss function is a function of two variables, Y hat sub I and Y sub I, but actually the Y sub I is given, so it's just a function of the Y hat sub I. And it's greater than or equal to 0 and equal to 0 only if the prediction Y hat sub I is a match of Y sub I. It's the penalty for a mismatch on an observation I, and we tend to only use convex loss functions. The cost of a classifier on a given set of data is the average of the losses due to mismatches. So cost is the average of the losses. It's a convex combination of convex functions, and therefore it's also convex. So sometimes we want to use binary labels of -1, 1 instead of 0, 1. Here I have a Y hat. These are predictions of labels, and a Y, which are the actuals. And notice we have some mismatches. The predictions are shown versus the actual labels. And notice the 0, 1 labels can be replaced by the -1, 1 labels. And we get something like that. So now -1 for negative and 1 for positive. And notice that if we have a match, then the product of the Y hat sub I and the Y sub I is 1, or in other words, it's greater than 0. If we have a mismatch, then the product is -1. Notice that in the two marked, the product of Y hat and Y is -1. The number of matches can be calculated from the products of the Y hats and the Ys. So when we use 0, 1, we tend to be working with probabilities. But when we use -1, 1, we tend to be thinking in terms of matches. So which labeling do we use? Well, it depends on the representation of the variable with labels of either positive or negative. So if we have 1, 0, true or false, then typically we're doing some kind of a probabilistic model optimizing some entropy. But we can and often do use binary labels of 1 and -1. So plus is 1, minus is -1. Both representations are useful. Which one to use? Well, that's part of the modeling process. In this video, we're going to focus on binary labels of 1 and -1. So we're using -1, 1 as labels for our responses, for our binary classifier. That means that the prediction Y hat sub I, the sign of Y hat sub I is a prediction of the class. Y sub I, the actual, is either a 1 or a -1. Therefore, the product of Y hat sub I and Y sub I greater than 0 means we have a match, and if it's less than 0, that product is, we have a mismatch. Accuracy is the number of matches as a percentage of the number of observations, and of course the goal is to minimize the number of mismatches. Each mismatch is an associated loss in accuracy, and cost is the mean of the losses for the given training data. So let's look at some loss functions, beginning with the 0, 1 loss function. So it's 0 when we have a positive product because it's a match. It's 1 if we have a negative product because we have a loss in accuracy. So if we define f(0, 1) of x to be the characteristic function of negative infinity 0, then the 0, 1 loss function is just this function f(0, 1) applied to the product y hat sub I, y sub I. And just looking at the loss function itself, it looks like this. It's 0 only if y hat sub I and y sub I are a match. The cost function associated with it looks like this. Notice the derivative is 0 everywhere the derivative exists. So let's get some smooth approximations to the 0, 1 loss function. So here's the hinge loss. It's the maximum of 0 and the negative of the product. So if the product's negative, then it's the positive product. So notation, this is ReLU notation, max of 0v, with a little plus as a superscript. And so this is what our hinge loss function looks like. And the f hinge is just negative x ReLU. And it looks like that. The cost looks like this. The least squares loss function, similarly, 1 minus the product squared, and notice that the corresponding f(ls) of x is 1 minus x squared. And there is our ls loss function. Here is the ls cost. Exponential is e to the negative of that product. The f function, therefore, is e to the negative x, and we'd have something like that. And in general, there are lots of different ways of defining loss functions, as you see here. So let's do a simple illustrative example using least squares loss. Our model has two parameters, beta naught and beta 1. Our data, x sub I, y sub I, is going to be these 5 points, and notice the y's are labels: false, 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 true. And we have 5 observations. All these f's correspond to negative 1, and the t is just going to be 1. The least squares loss function is 1 minus y hat sub I times y sub I squared. And this is just a simple example, 2 parameters, nothing significant going on. I'm just illustrating the ideas. So this is my cost function, and this is what it looks like when we write it out. So in summary, this is what we have. And let's look at our least squares cost function. Notice that the losses are convex as functions of beta naught and beta 1. And therefore, this least squares cost as a function of beta naught and beta 1 is a convex combination of convex functions. Therefore, it's convex. So therefore, we can find the minimum if we just take the derivative with respect to the parameters and set that equal to 0. So we take the derivative with respect to beta naught, which is this summation. And notice we get from the chain rule a negative y sub I at the end. We distribute it through, but that gives us a y sub I squared, but y sub I squared is equal to 1. And therefore, we simplify to this expression, expand that out, and notice the 1 over m sum I equals 1 to m of 1, that's just 1. And this term with the x sub i's is x bar, and this term with the y sub i's is y bar. So we have the derivative with respect to beta naught looks like this, and it's equal to 0 when beta naught is y bar minus beta 1 x bar. Now let's take the derivative with respect to beta 1. Once again, we have the chain rule, negative xi y sub I, and we expand out. We've got another y sub I squared. We also got a beta naught we can substitute for, which gives us this expression. Do a little bit of algebra. And then we can see that it's equal to 0 when beta 1 star is equal to this summation over the x sub i's times y bar minus y sub i's over the summation xi's times x bars minus x sub i's. And then once we have the beta 1 star, we can get the beta naught star. So here is our result. It tells us that y hat is beta naught star plus beta 1 star times x, but we use our result for beta naught star, or we could write it, our model, in this way. Here's our data now with the negative 1, 1 labels. Here is the result of applying the model to the x's to end up with actual and the predictions. Notice that the y hats from the model are negative where the actual are negative and positive where it's positive. So a loss function is a function of the predictions, and the predictions come from a model with parameters. The cost function is therefore a function of the parameters, which looks something like that. And if we put in the actual training data, the M observations, we end up with our loss function actually has this form. It's a function of the parameters. And the best parameters are therefore the ones that minimize cost, but notice that the cost is a convex combination of the losses. Therefore, it's an expected value of loss, but only if we have a certain process that we use. We pick I independently, uniformly, randomly. We sample it from 1 to m. We do this some number of times, and the expected value of that process for the losses gives us the cost. In other words, cost is expected loss, but that means the gradient of the cost is the expected gradient of the loss. So what if we use algorithms of this form? For some max number of iterations, uniformly randomly sample I from its possible values, apply the model to the observation to get the prediction, calculate the loss for that observation, differentiate the loss with respect to the parameters, modify the parameters so the gradient of the loss is closer to 0. This is what's known as a stochastic approximation. And if we do that, then minimum cost is produced by this stochastic process of minimizing loss. Diagrammatically, remember the forward direction for Frick's parameters is y hat, and the backward direction minimizes loss. We calculate the loss function, and then the loss function is a function of the parameters. So we take the derivatives and we use that to minimize the loss. But remember, we're looking for the true model, which has no parameters and tends to be incredibly complex. Our goal is to approximate it with our model. But that assumes that the model can approximate the true model. Most models are not capable of approximating the true model. A high bias model, if we're trying to approximate a complex low bias F-true, is probably not going to give us a good result. Those capable of doing so uniformly over a domain D with any epsilon greater than 0 are called universal approximators. So let's look at this idea a little more closely. Typically, we know very little about the true model. We do not know what form or properties it has, but very often we know, or at least we can safely assume, that there is a vector space of functions, script V, for which the true model is in that vector space. At least this definition. A parameterized model is a universal approximator over script V vector space of functions if for all G in script V and epsilon greater than 0, there's a set of parameter values, beta hat, such that the function model with those parameter values, beta hat, minus the G in V is less than epsilon, and that's uniformly over X in D. For example, Taylor series are universal on the vector space of real analytic functions over R. That's because analytic functions can be represented by a Taylor series, and therefore they can be approximated by Taylor polynomials. Fourier series are universal approximators of real functions continuous over an interval. But linear transformations cannot universally approximate over many types of vector spaces of functions. So if we have a model with parameters beta that can universally approximate over script V vector space, then it's called a universal function approximator, UFA, on that script v vector space. In this module, we will actually meet our first universal function approximator, which is an ensemble method known as a random forest. And deep learning is based on UFAs as models over highly complex vector spaces. And such UFAs will often be several convex and linear layers, convex functions and linear functions, with a final layer, which allows the construction to be universal. So loss functions and cost minimization. We're doing predictive modeling via convex optimization. Loss functions convex in the parameters of a model. Cost functions that are convex combinations of convex losses. The key concept is the goal is to minimize cost, and another key concept is that cost is expected loss. And therefore, our key practice is algorithms based on individual losses which stochastically imply minimized cost. Stochastic means via averages over max iterations, which is known as empirical expectation.